Good day and welcome to our Ansys CFX and Flownex coupling webinar. Our guest speaker today is Dr. Andreas Spille, Managing Director of CFX Berlin. Andreas, thank you for joining us today.
Hello, Marinos. Thank you.
Your hosts today are myself, Marinos, and Willy, our simulation design engineer. Hello, Willy.
Hello, Marinos.
So, Andreas, let's start by you telling us a bit more about CFX Berlin and your partnership with Flownex.
So I start with a short introduction to CFX Berlin. We started in 2001 with main focus on the 3D CFD software CFX. We became a channel partner of Ansys then, and now we also sell Fluent and a lot of Ansys products for structural mechanics and electromagnetics. On the application side, we have a focus on turbo machines and positive displacement machines, and develop and sell our own product, TwinMesh, for the meshing and automatic setup of these machines. And as you know, CFX Berlin is a reseller of Flownex in Germany.
Thank you, Andreas. To also add to that, Flownex also has a component that allows coupling of the Ansys CFX and Flownex solvers.
That is correct, Willy. Our companies work closely to develop this interface.
Thanks, Andreas. So let's continue with acknowledgement to CFX Berlin for the work done previously for the 2018 ASME Turbo Expo. We will be using this collaboration with Flownex and the two examples as the technical case studies for the webinar today. The references are shown on your screen for further reading. Willy, do you mind giving us a quick overview on Flownex?
Sure, Marinos. Flownex is a one-dimensional thermohydraulic solver that solves for flow and heat transfer. Flownex also solves the conservation equations considerably faster than 3D CFD due to the 1D nature and is therefore used for systems analysis and control optimization. Flownex is also developed in a NQA1 and ISO 9001 environment to ensure the quality of the software.
Thank you, Willy. And also, Andreas, your overview of Ansys CFX and TwinMesh.
Ansys CFX is the three-dimensional CFD solver that specifically addresses complex flows such as one would typically encounter in turbo machinery. And TwinMesh provides an automatic workflow for structured mesh generation and the CFD analysis setup for rotary positive displacement machines.
Now, two benefits of using a co-simulation approach really stand out in the turbo machinery examples. The first is it is possible to define component boundary conditions better in the 3D CFD case, and this is done by dynamically obtaining boundary values from the 1D system and transferring it to the 3D model, instead of a static definition of the boundaries. Secondly, the co-simulation reduces the required mesh count, thereby saving time and also keeping accurate results. Significant improvement in solving time compared to modeling the whole system in full 3D. The first of two applications that we will be looking at in this video is a vacuum vane pump. Willy, could you please give us a little bit of background on this type of pump?
Sure, Marinos. A vacuum vane pump works through a rotating axis where the volume of the fluid is reduced and increased during a rotation. This causes a vacuum at the inlet and the pressure rise at the outlet. Furthermore, the rotation of the pump is generally above 2,500 revolutions per minute, so there is a significant number of pressure fluctuations over a short period of time.
This seems to be quite a complex component and also an ideal component to then be modeled in Ansys CFX, right, Andreas?
That is correct, Marinos. Specifically, the complexity of the component and speed at which it rotates. Ansys CFX can model the component given a fine mesh and small time step sizes. In this investigation, we used a quasi 2D mesh to model the geometry of the pump. Furthermore, as Willy explained, there are pressure fluctuations that propagate from the pump. The boundary conditions will be influenced by the pressure fluctuations and may not capture this effect correctly unless the system response is included in the model.
So, Andreas, how can we include these system responses without increasing the mesh count and therefore increasing simulation time?
Well, Willie, with co-simulation between the two codes, Ansys CFX and Flownex.
So, to understand the co-simulation methodology, there is bidirectional information exchange between the Flownex and Ansys CFX solvers.
Marinus, to further expand on the bidirectional information exchange, Flownex and Ansys CFX has seamless integration with a dedicated CFX component in the Flownex library. For this specific application, the upstream and downstream pipes were modeled in Flownex, where Flownex sends pressure and temperature boundary conditions to the inlet of the VANE compressor, and CFX sends mass flow back to Flownex as well as a temperature at the positive mass flow boundary condition. Data is exchanged after each time step.
Well, that seemed quite straightforward to set up. Andreas, we talked about the pressure fluctuations and pulsating flow. What are the physical effects on the simulation?
We looked at two scenarios where we have a coupled and uncoupled flow simulation. In the first uncoupled scenario, we can clearly see that there are high mass flow variations as rotation occurs. The standard static boundary conditions on Ansys CFX are reflecting pressure waves and causing high flow variations, often leading to standing waves between the machine and the boundary. In the second scenario, we have the co-simulation between Flownex and CFX, where we can see that the fluctuations have leveled out and we can see a more realistic behavior from the pump. Depending on the boundary conditions at the Flownex boundaries, we might still have reflections there, but these are then of a physical nature and not purely numerical.
This is very interesting, Andreas. I can definitely see the benefits of having system boundary conditions for a wide variety of applications.
In this next slide, we can see some detail regarding the mesh. A fine mesh is required for the vane pump in order to capture the complex flow in the component, especially the gap flow between the vanes and the casing, and the opening and closing of the chambers towards suction and pressure side. In our specific application, we use a quasi 2D mesh with a hex cell count of approximately 45,000 cells. Due to the complexity of the pump, a relatively fine mesh is required. Furthermore, small time steps were used due to the fast rotating speed and quick pressure changes in the pump. As seen in the animation in the bottom of the screen, a time step size in the order of 10 microseconds is required to capture pressure fluctuations correctly. Here, 70 microsecond time step size for 2380 RPM. Additionally, a test was performed where the pipes have been included in the CFX model. It could be found that without co-simulation, the time to convergence takes up to 30% longer compared to a co-simulation between the two codes.
I can now imagine that with the fine mesh and the small time step size, any addition of more components such as valve or restrictors and even flow distribution downstream of the pump will have an adverse effect on the time of the simulation if co-simulation is not done. Looking at the results from this successful co-simulation, we are able to not only reduce the mesh size and increase the speed of the simulation, but also provide more realistic and dynamic boundary conditions to the Ansys CFX component model. Furthermore, through co-simulation, we can now extend the system by including other flow components such as valves, flow resistances, and flow distribution to capture the effect of the system as a whole. Right, in the second example, we can now showcase in our co-simulation offering is that of a rotary screw compressor. Willie will provide us with a quick background on this specific application.
The rotary screw compressor is another complex system where flow is being forced through the rotors. The compressor presents a complex geometry, which is an ideal simulation case for Ansys CFX, keeping in mind that a fine mesh and small time step sizes are required to accurately capture the fluid dynamics. To increase the complexity, we would like to include operational scenarios such as a valve opening on the downstream side of the compressor. Again, the solution is co-simulation between Flownex and Ansys CFX with additional Flownex components such as valves.
So Willie, just to expand on this specific application, co-simulation between Flownex and Ansys CFX provides the ideal environment to do virtual system prototyping of any system.
That is correct, Marinus. Specifically, operational tests like this can be done, and component design can be done more effectively as the component is tested within a system environment.
I will take us through the results. We can see that the system initialized at 1 bar. After 4 rotations, the downstream pressure of the compressor reached 3 bar, at which the valve opened. A slight drop in pressure occurred, and fluctuations in pressure as well as mass flow could be observed when looking at each point in the system. Typical scenario testing like this can be performed with even more complex systems without an adverse effect on simulation time.
Thank you very much, Andreas and Willie. To conclude our co-simulation webinar for today, co-simulation provides a unique systems-level modeling solution where Ansys CFX and Flownex can couple easily and seamlessly.
Yes, Marinus, this allows accurate simulation of complex component details in 3D with Ansys CFX, while modeling 1D flow and heat transfer, still with high fidelity in Flownex.
Furthermore, you can include reduced order models in Flownex, obtained from Ansys CFX, to provide a digital twin environment for fast and accurate system simulation.
The benefits of this capability is clear, reducing mesh sizes for the same system, thereby increasing simulation speed. Also, the dynamic effects of system boundary conditions are included, such as pressure waves, which enables the study of various scenarios, such as startups and shutdown events. So, thank you very much for joining us and watching this video, and a very special thanks to Andreas from CFX Berlin and also to Willie.
Thank you, Marinus.
Thank you.